Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 4, and we are in part 6 of chapter 2. We have been discussing hypothesis testing. We have actually performed 3 hypothesis tests using the same data. So there is one last case that would be a possibility for testing data, the 2-sample case, and we have not looked at it. In order to do so, we need to make some modifications. I've put those here in blue. So we need to have N1 and N2 equal to 30. So N1 equals N2 equals N equals 30. Okay? In order to use the central limit theorem. So for each population, which we're assuming this sample comes from one population, the new recipe, and this sample comes from the second population, the original recipe. And so in order to estimate the normal distribution using the central limit theorem, we have to have n equals at least 30 in each of these samples. So this is not going to be some results that we can compare to the other results we've gotten so far. The other results we've gotten so far were using n equals 10 and the variance that was given in the actual experiment. Since I don't have any actual data points, additional actual data points to put into here, I had to make some modifications. So I could have chosen to leave the variances alone, but when you have more data, it's often the case that you'll have a slightly bigger variance because you have more chance of getting more extreme data points. Okay, so you could have a larger variance. I wanted to keep the ratio of variance to sample size the same, so I modified the variance in both of these along with the sample size. So when we use the CLT, we would say that X is distributed, or has a distribution function. We don't know what it is, f of X with mean, mu, and standard variance, sigma squared of X. Mu of X, sigma squared of X. Then X bar is approximately normally distributed with mu of X and sigma squared of X over N as the variance of the X bar. That's the central limit theorem. So for a large enough N, the distribution of X bar is approximately normally distributed. We're going to use that fact, and so we can use, with our test statistic, we'll use a Z for the standard normal. The hypothesis statement is not really changing. I did need to change the number of samples, so we still have the same statement, mu1 minus mu2 is 0, mu1 minus mu2 not equal to 0, the two-sided test, or two-tailed test. Using the model doesn't change except that I equals 1 and 2, and now J goes from 1 to 30 instead of 1 to 10. And then alpha is still at 0.05. Now we've worked with these values several times, so again I'm not going to take the time to actually plug in this case because that's not the interest. We've gone through how to plug into the values into the formula, so you should be able to do that. So please pause and do that in this case. Now that you've started back up, let's talk about the results. So here we obtained a test statistic Z0 equal negative 2.88. We need the critical region, so that is in the table that I've provided. We have a not equal to. We have large N, so N is greater than or equal to 30, and so we can use this statement as our critical region or rejection criteria. So we need to write the whole statement every time. Z0 less than negative Z sub alpha over 2, or Z0 is greater than Z alpha over 2. Alpha over 2 is 0.025 for our case, and in most cases in this book we will do that, but you need to know it may change in some cases. All right, so Z of 0.025 is what we're looking for. I want to recall that for the Z distribution, standard normal, if I have a critical value, z of 0.025, by definition, the area above is 0.0250. So the area in the cumulative distribution, the table that we have in this book, is only cumulative values. I need 1 minus 0.0250 equals 0.9750. I need to find that value inside my z table to find my critical value, z sub alpha over 2. So here is 1.9. And it turns out that 0.975 is corresponding to a z value of 1.96. So our critical value is 1.96. Now we can plug that in to our formula. Since we have a negative here, we only need to look at the negative portion of our critical region or rejection criteria. Because we don't have a positive z naught, we don't have to look at the positive side. So we have a negative 2.88 is less than negative 1.96. This is a true statement, so we will reject the null hypothesis. Before we move on, let's look at the p-value. And for the z-table, we can find a fairly accurate p-value. We're looking up 2.88, so what we want, 2.88, since we have positive in the z table, we can look up that. We need the probability that z is greater than 2.88, but we also need the corresponding probability that the probability that z is less than negative 2.88, because we are talking about the claim with a not equal to sign in there. We're interested in both small and large values. So we've split up alpha into half and put half on one tail, half in the other tail. So when we find a probability for the p-value, we have to multiply it by 2 times the value that we're going to find. So we look up 2.88 in the table, 2.8, and this table is kind of split, so we look up here for 8. 8 is this column here. And so it turns out that the area below 2.88 is 0.9980. So 0.99807. So this area is 1 minus 0.99807. I'm sorry, not 07, 01, 801. Looking at the wrong, I'm not looking at the number I circled. So the circle 99801, which is 0.00199. So that's the one-sided. So we have 2 times 0.00199 equals 0.0038 something. Let's see, 98 or something. So 1 minus 0.00199, or I'm sorry, 0.00, yeah, 1 minus 0.99801 is 0.00199. 2 times that is 0.00398. Yes, just wanted to make sure. So that's our p-value, much less than alpha of 0.05, so we would definitely reject the null hypothesis. Okay, so that was our decision for both methods. They will always agree unless you make a mistake. So reject the null hypothesis. Therefore, there does exist sufficient evidence to support the claim, not the null, but the claim. We've written the claim. The addition of the polymer latex emulsion during mixing resulted in a different tension bond strength compared to the original formulation. We used alpha equals 0.05 or a 95% confidence level. The test was performed using a random sample of N1 equals N2 equals 30. Okay. Now I made the mistake of repeating an analysis that we had already done, so I will skip over that and go to the summary. We've used all 4 methods that I've discussed so far. The first case was where the variances were known. We said sigma 1 equals sigma 2 equals 0.3. I think it was squared. It was either sigma 1 or sigma 1 squared. I forget which. I think it was sigma. Just sigma equals point. That makes sense. So sigma 1 equals sigma 2 equals 0.3. And with that, we ended up with a test statistic of negative 2.09, saying that the variances were actually known and equal. And, known and equal. And 1.96 is our critical value. This statement is true, so we reject the null. We looked up the p-value, it's 0.0366. Now, what we just did in this video is looking at a case where the n was greater than 30. But remember, I had to modify the values, so this can't really be compared to the other methods here because it has a different sample size, and it's not based off of actual results. It's based off pretend results. Okay. With this case, I came up with a negative 2.88 for a test statistic. Definitely rejected H naught, and this was actually 0.00398 for the p-value, so fairly extreme. If I had not modified the variances, this would have been an infinitesimal, a really small number, not infinitesimal, but very small number, so it would have been highly significant. So with the same values of variance and a tripling the sample size in each sample, it really makes the rejection easier, is what happens. The test statistic becomes very extreme. Okay. All right. So variance is unknown but equal. So in this case, we would have had to have performed a test for equality of variances and said that we're comfortable that they were equal. And then our degrees of freedom are n1 plus n2 minus 2 are 18. And we obtain the test statistic of negative 2.207. The critical value with degrees of freedom of 18 is negative 2.101. Again, we reject, and our p-value we said was somewhere between 0.02 and 0.05. Okay. When we don't know the variances and we cannot assume that they are equal, we use Welch's t-test, and that is where we have to calculate the degrees of freedom with Satterthwaite's approximation for the degrees of freedom. And in that case, we ended up with a degrees of freedom that was very close to 17. Now, because the sample sizes are equal, these two numbers, the test statistics equal, but the critical values are different. And this is supposed to be a negative 2.100. So typo, sorry about that. And this is still a true statement. But notice that this value is further from this than this value is. So this would actually have a lower p-value, or a larger p-value, worse or larger p-value. So it's, in other words, it's more difficult to reject when you have a lower degrees of freedom. Okay, it's a more conservative test. Okay, so it's really important that you know whether or not the variances are equal or not, and that will affect, in some, if this had been a borderline case, it might be the difference between rejecting and not rejecting the null. Okay, again, the p-value is between 0.02 and 0.05, but it would be closer to 0.05 in this case than in this case. Okay, so that is how we do those tests. I do want to talk about the robustness of the test. Okay, and this is talking about the violation of the assumptions. So, 1, small to moderate. This is very important. Violations of assumption of normality will not seriously affect the results. Any failure of independence cannot be ignored, though. Okay. So if we assume that these are normally distributed, then to be independence, R must be close to 0. If it's not close to 0, then, well, okay, let's be careful with this. Over time is what we're talking about. So we should not see a trend over time. Okay? They should be independent. And how we can get rid of this is by randomizing the order in which the batches are run. So each time we create a batch, before we do that, we randomize the from 1 to, if we have 1 to 10 and 1 to 10, say we have 1A, 2A, up to 10A for the first formulation, and 1B up to 10B for the second formulation. We take those numbers and use a random program to randomly order them. And so that is how we perform or how we create the batches and perform the order in which we perform the test. That will prevent us from having dependence across time. Okay? So the randomization is extremely important. If you don't do that, your results will be garbage in most cases. Okay? And we don't want that. What that means is you may come up with the results, and it's true for this case, but the next time it might not be true, depending on the order. Okay, and you don't want that. If you have questions, come to virtual office hours. If you need help before you can come to virtual office hours, by all means email me. I will get back to you as soon as it's possible. Please take care of yourself. We hope to see you next time.